Now let us discuss what a system means. All of us intuitively have an idea what a system is, constituted through its usage in everyday terminology. We may formally say a system is a collection of components. Okay, so put together to serve a particular purpose. So these system components are unified through some kind of interdependence among them. They react with each other, so the whole system functions as a whole to serve a particular purpose. Therefore, physical systems in the broadest sense are an interconnection of components, devices or subsystems. So in contexts ranging from signal processing and communication to electromechanical motors, automotive vehicles, then chemical processing plants, and so on. Therefore, a system can be viewed as a process in which input signals are transformed by the system. Okay, so input, you are giving something that is called signals, and that signals are transformed by the system, or it can cause the system to respond in some way, that is resulting in other signals as output. Sometimes the system responds okay, and it gives the output, or input is signal and output also can be a signal. Okay, for example, if you consider a high fidelity system, high fidelity audio system, okay, that system takes the recorded audio. You feed the recorded audio as an input, and it okay, and it generates a reproduction of that signal. So then the same signal is reproduced here and given to the speaker through an amplifier. Okay, so if the hi-fi system has tone controls, we can change the tonal quality of the reproduced signal. Okay, so in this high fidelity system, if you have some tone control like bass and treble, okay, then you can control the tone quality of the reproduced signal. Similarly, let us consider the circuit. Let's say you have input voltage Vs, and this drives the resistor R and a capacitor C. The voltage across the capacitor is Vc and the input voltage Vs. The current flowing through the circuit is, let's say, I. and this can be viewed as a system with input is voltage, and that voltage is Vs, and the output is also voltage, but now it is voltage across the capacitor, let us say Vc of t. Okay, like that we can now give a number of examples. Okay, even you can give some more examples also, like a power system, right, or the natural educational system, hospital systems, railway systems, transportation system, and so on. Okay, so all these are constituents of systems. So therefore a system in general is a collection of objects united through some form of interdependence among the various components. So interdependence is among subsystems, as you may call. Now the variables that describe the status of these various components in a system may be quite diverse, depending upon the nature of the component, the nature of the system, and so on and so forth. For example, if you are talking about electromechanical systems, you may have the electrical variable like voltage and currents associated with the electrical component as an input, and mechanical variables like force and velocity, which describe the status of the mechanical component at the particular point in the system. So voltage and currents, okay, associated with the electrical components. Similarly, you can have mechanical variables like force and velocity, which describe the status of the mechanical components. Therefore, a system is an omnibus type of concept, which includes the whole variety of situations that one can come across. Now, while analyzing these systems, the first step usually is to model the system. The first one is we need to model it. So that is mathematical modeling. Okay, so this modeling is done in terms of idealized components, okay, which are put together in a particular fashion. So for modeling we use idealized components. We may use resistor, we may use capacitors, we may use inductors or something else. So this evolution of the model is done with the two conflicting requirements in our mind. Okay, so generally when you try to model, two ways you can model, and these two ways are conflicting with each other. The first one is you can model with approximately. Okay, so we would like to have a model as realistic as possible so that it simulates the real system. So one is exactly you can model, and another one is approximately you can model. Each of them has its own pros and cons. If you try to model exactly, then the model will be very complex. If you try to model it approximately, the model will be very simple. But of course, even though it is complex, it gives a accurate result. and here it is simple, the model will be simple, but you will get a not accurate result, approximate result you will get it. So the result is not accurate. So each of them has its own pros and cons. Therefore, we would like to make the model as complex as possible to get the accurate result. If you make as complex as possible, then we lose as little information about the system as possible. So we will not lose much information. Accurately, we will get the result. It's up to you what type of modeling you want to do it. Like it is again comparing your iPhone with your normal Chinese mobile phone. Okay, so iPhone, if you buy some, the rate will be around some more than 40k or something. I think minimum rate is some 30 or 35k thousand. But Chinese phone you can get 8,000, 9,000. So how accurately you model the device and what quality of components you use, how they are connected. So it depends many parameters. So the audio quality is very good. If you buy iPhone, audio quality is good, video quality is good, display is good, its life is high. But a Chinese phone you cannot expect all those things. So because they use very good model in this one. Similarly, on the other hand, we would like also to make model as simple as possible, like Chinese mobile phones, to lend itself to convenient mathematical analysis, so that the person who use this approximate model for analysis and synthesis will retain a sanity, in the sense because it is going to be a huge because when you use a huge complex type of model, you will never be able to solve it. Okay, so when you try to model very accurately, then you will be having lot of constraints and a lot of variables. So in that case, it's very difficult to solve it. Therefore, there are two conflicting requirements. When you go to an industry, two conflicting requirements will be given. So another one, first one is approximate model, and the other one is complex model, accurate model. Okay, so there are two conflicting requirements in the evolution of a model for a given physical system. Okay, on one hand, it should be as complex as possible, so that it will lose as little information about the system as possible. At the same time, it has got to be simple enough to be lend itself to convenient mathematical analysis. Now, very often we refer to the model itself as system, even though we must always keep at the back of our mind that the model is a mathematical representation of a system. As I said, model is a mathematical representation of a system. So the first step is you have to model for a given system. Okay, concept to model, and model to mathematics. It is an idealized representation. So the actual physical system is something different. Okay, if you model it, then the model will not be the same as it is when you go and compare with the physical systems. So in some ways, the physical system characteristics may not agree with the model. Even if you develop a model, sometimes the physical system characteristics may not agree with the model. And if it is so, what will you do? Then we have to refine the model. Okay, change the model, tweak the parameters, do slight changes here and there, and finally you arrive or you make it more realistic and more accurate model. Okay, so wherever it is warranted. Now, in arriving at a model for a particular system, the derivation of a model is specific to a particular discipline. like mm, you must study the physics of the situation, you must know the characteristics of those and arrive at a suitable model. But once we have evolved a model, then a whole lot of systems can be analyzed through a common framework. I mean, a common set of mathematical tools which can be used to analyze a whole lot of these different system models. Okay, so we have many tools which are available to analyze the systems. So first system, and then we should know the functioning of the system concept, then model, and this model can be analyzed by using mathematical tools. There are many tools like continuous time Fourier series, discrete time Fourier series. If the signal is continuous time periodic, then you go to continuous time Fourier series. If the signal is a discrete time periodic, input signal is, then you go to discrete time Fourier series, continuous time Fourier transform, then discrete time Fourier transform DTFT, then discrete Fourier transform, Laplace transform, Z transform. There are many tools which are available to model this, to analyze these systems, because after all model is a mathematical equation, right? That equation governs the operation of these various systems, okay, which are more or less the same. Therefore, there is a unifying body of techniques and knowledge which come under the general title called system theory, or principles of system analysis. Okay, which will be the main scope of our study in this course. Then let us talk about continuous time system now. As I said, there are two types of systems. One is CT system. CT means, what I mean is continuous time system. Then you have discrete time system. Okay, so continuous time system is a system in which continuous time input signals are applied. Okay, and due to this continuous time input signal, the system gives an output, and that output is also continuous time signal. Okay, so such a system will be represented like this. So the input is denoted by this arrow mark. Let me call the input is input by x of t, and the output is denoted by y of t. So either you can represent through this method called block diagram representation. Can put a block and you can say the input is x of t and the output is y of t. Alternatively, we will often represent the input output relation of a continuous time system by the notation like x of t, put an arrow mark, and y of t. That means the input is x of t and the output is y of t of a system, continuous time system. By the same token, we can define discrete time system as follows: DT system, discrete time system. So discrete time system is a system that transforms discrete time inputs to and into a discrete time outputs. Okay. The output is also a discrete time signal. Input is denoted by x of n and the output is denoted by y of n, like this. Symbolically, you can write x of n gives rise to y of n, like that. Let me consider a simple example, the same which I already given in the beginning of the lecture, that you take a source Vs and this source drives the resistor in parallel in series with a capacitor Vs. The voltage across the capacitor is Vc and the input, this is the input voltage, by the way, input. Let me call, I am going to take the voltage across the capacitor, so it is my output, and the current flowing through this capacitor is I. So this is the RC circuit because it contains only resistor and a capacitor. So therefore this is called a RC circuit. And V of Vs, let me take this Vs as a function of time. Let me put Vs of t, small vs, small letter, to denote time varying signals. Generally we reserve capital V, capital I, this and all reserved for DC quantities, direct current quantities, and small letters, small v, small I, this and all reserved for time varying parameters. Therefore instead of writing Vs, then let me put V suffix s, small vs. This represents the time varying voltage. I mean the voltage is a function of time, that's all. And this one also let me remove and put small vc of t. Now we can use simple circuit analysis to derive an equation describing the relationship between the input and output. What is the input? Input is V suffix s of t, input voltage, and the output is V suffix c of t. Now we can derive an equation which gives the relationship between the input and output. Okay, let us derive the equation so that we can describe the relationship between the input and output. So specifically from Ohm's law, the current I of t through the resistor is proportional to 1 by R to the voltage drop across the resistor. Okay, so voltage drop across the resistor is Vs of t minus Vc of t proportional to 1 over R. Vs of t minus Vc of t divided by R. So by using Ohm's law, you can write down the I of t. Or if you are familiar with Kirchhoff's voltage law, then also you can apply. So generally I follow one technique, like let us take, this is like a road, it's a closed path road, like this. Okay, like this. Okay, you take a bicycle, start from this point, keep on drive on this path and come back to the place where you left. So you start from here, and now when you are riding by bicycle, you see a resistor here. In front of you there is a resistor. When the current enters, that entering point is positive. It develops voltage with a positive polarity. And when the current leaves, that is negative polarity. Similarly, here also the voltage enters, so positive, and leaves, that is negative. So when you come to this point, then again you are looking positive polarity. So whenever you see a device, then find the polarity of that device. And again come here. If you are coming here, then again you are looking a source, and the source with a negative polarity. So whatever you encounter, just write down in the equation. In the closed path by Kirchhoff's voltage law, the sum of potential rise will be equal to sum of potential drop. So you start from this place, and first you are looking at the resistor. So voltage drop across a resistor is current times I. So I of t times R. Then again you are coming. Don't ask me why this minus I should not take, because when you see a device, then you look at the polarity. And the conventional rule says the current entering point is positive. Plus you are looking at a positive polarity. That's why I put plus here. And then voltage drop across the capacitor is Vc of t. Okay, and again when you come back, you keep on come like this, come here, and you are looking at minus sign. So I put minus here, minus of Vs of t, which is equal to 0. Now rearrange this equation. So I of t times R is equal to Vs of t minus Vc of t divided by R. So this is the voltage drop across the resistor. Now what we want is, we want current I of t, which is, sorry, this R will not come, Vs of t minus Vc of t whole divided by R. Okay, so this is a voltage drop of current flowing through the resistor or through the circuit. Similarly, using the definition, you are using the defining constitutive relation for a capacitor, we can write I of t, because I of t is the amount of current which flows through the capacitor, and the current flowing through the capacitor is given by d times dVc of t divided by dt. Okay, so now I of t I got it. Now you substitute back there. So C times dVc of t by dt is equal to Vs of t minus Vc of t over R. Now bring back this capacitor to the right hand side denominator, then d times Vc of t divided by dt is equal to Vs of t minus Vc of t divided by Rc. Now again rearrange this, Vs of t divided by Rc minus Vc of t over Rc. This is dVc of t by dt. Now which is input and which is output? This quantity is input, right? And which is output? Voltage across the capacitor is the output. That's what we assumed. So bring all output quantity in one side and input quantity to the other side. Therefore, derivative of Vc of t plus Vc of t over Rc is equal to Vs of t over Rc. Okay, so therefore we obtain a differential equation okay, describing the relationship between the input Vs of t and the output Vc of t. Now once you solve this equation, then you will get the output value Vc of t. You can get it. Okay, you find the natural solution and then complementary solution. Make a Vs of t equal to 0 and find the solution, and then make a Vs of t not equal to 0, and then you can find out the other solution. Totally you will get a that means particular solution. So the total solution is going to be natural solution plus particular solution. So later on we will study some transform techniques like Laplace transform. In one step you can get the answer, no need of doing all these things. You might have studied in the school, like solving differential equation is not that much easy, but once you start to use the tool, then you love it. You can easily solve the differential equation. It is very easy to solve the differential equation. So no need to break your head by thinking about how can I find out particular integral, then how can I find out natural solution, this, that, how can I find out the roots, factors. Then it's a lengthy and a complex process. But the moment you start to use tools like a Laplace transform or Z transform, for difference equation we use a Z transform, for differential equations we use Laplace transform. So the solution will be very easy. Simply you transform into the S domain and you can get the answer. Okay, so let me stop at this point. In the next class we will talk about interconnection of systems, how the systems are interconnected in order to get the overall thing which we wanted to, which we want the system to be done. Okay, so how the systems can be interconnected, how will you connect, either will you connect in the series fashion or parallel or in the complex method, or how you connect, how do you find out the overall response. So these are all things that we need to discuss. So let me stop at this point. Thank you very much.